Let's look at figuring out how much materials can change in length when the temperature changes. So here's this chart we saw last time, and what are we going to do with that? There is a simple formula that we use, and there's a bunch of Greek letters in here. There's delta, the change in length. You might remember delta from when we talked about deformation and strain. There it is again, deformation, change in length, equals the coefficient of expansion, and that's a Greek letter alpha. See how it kind of looks like a lowercase a? So that's the coefficient of expansion. These are all the coefficients. So you find the one you want to use and you plug it in there. There's the length and there's the change in temperature, delta T. So the coefficient out of that table, the original length you're starting with, and the change in temperature in degrees Fahrenheit if you're using this chart. So here's our thermal expansion and contraction formula. And this expansion or contraction happens in a linear direction. It's inches per inch. So a little short direction will only expand a little bit. A big old long length will expand more because it's inches per inch. And it doesn't matter how wide or what shape it is. It's just inches per inch. So let me back up here just to look at these coefficients. These are written in engineering notation. So here's steel, for example, 6.5 times 10 to the minus sixth. Let's review what that means. If you have 10 to the first, that's just plain 10. 10 to the minus first is 1 over 10. So if you had 6.5 times 10 to the minus 1, you would move the decimal point one place to the left. 10 to the minus 2 is 1 over 100. So if you had 6.5 times 10 to the minus 2, you would move the decimal point 2 places to the left. And see that number? That's what we got there. If you have the coefficient that we're working on, 10 to the minus 6, 10 to the sixth is 1,000,000. 10 to the minus 6 is 1 over 1,000,000. What do? We take that decimal point, and because the exponent is a minus 6, we move that decimal point 6 places to the left. And what you come up with here is a point, 5 zeros, and then the 2 numbers. Now, your calculator probably has an E for exponent key on it, or EE key, and you can use that and just punch in the minus 6. If that bugs you and you don't like it, you can always actually punch in 1, 2, 3, 4, 5 zeros if you like. Well, let's think about, this is our first quiz question, I believe, and it's an imaginary example totally made up just so we can begin thinking about it. This material, I gave it a thermal coefficient of expansion of 1/16 of an inch per inch. That's just ridiculous. There's no material that has a coefficient that big, but I'm just trying to get us warmed up here. So every material its properties are stated as of 68 degrees Fahrenheit. And tools are calibrated at that temperature, measuring devices are calibrated at that temperature. That's the standard temperature. Okay, so let's think about, we got this bar, and when the temperature is 72 degrees Fahrenheit, how much will the bar expand in inches per inch? All right, so how much different is 72 from 68 degrees? 72 minus 68, it's 4 degrees warmer. So 4 times 1/16 is 1/4. 0.250. So for every inch at this temperature, for every inch, that bar will expand 1/4 of an inch. So let's think about the different sides of this bar. The 2-inch side will be 1/4 of an inch times the length times delta T, change in temperature. So the 2-inch side will get 1/2 inch wider. The 4-inch side will get same numbers, but now the original length is 4 inches, so it will get 1 inch deeper. And the 100-inch side, same numbers, but the original length is 100, so that side will get 25 inches longer. Again, totally ridiculous, made-up coefficient just to make a point. Well, let's think about something from the real world. You've got a steel tape measure, let's say, and you're out there measuring your driveway in the heat of August. It's 108 degrees Fahrenheit. Now this tape, as all tapes are, this tape was calibrated at 68 degrees Fahrenheit. How much hotter is it now than it was when it was calibrated? It's 40 degrees Fahrenheit hotter. And what is the coefficient of thermal expansion for steel? It is that number. We looked it up in our table. Okay, so now let's work towards plugging our numbers in. First, they give us the length in feet, 50 feet. How many inches is that? 50 times 12 is 600 inches. So let's figure out how long will the tape be at that 50-foot mark. Here's our equation. The change in length is, there's our coefficient. 600 is the original length. Delta T is 40. So the change in length will be 1/56 of an inch. Thinking about railroad tracks, this is out of an interesting book called The Railroad, What It Is, What It Does. And he's talking about what happens to rail that's laid at a temperature in the summer when it's hot, 1,500 feet long. What happens when the temperature is freezing? Well, there's the coefficient. 1,500 feet is 18,000 inches, and there's delta T, 100 inches. So that thing will shrink 11.7 inches. He got 11.5. He might have rounded. And so he talks all about how much stress is that, which you are in a position to understand now because you know all these vocabulary words. Speaking of rail, here's a picture out of a physics textbook of a rail that was laid in the cold weather, mistake, and in the hot weather it expanded, and this is what happened. And then here's a news report. This is out of the Eugene paper some years ago. Train derailed back east, and the forensic engineers determined that it was because of thermal expansion. They had laid the rails in cold weather, and so in hot weather they expanded. Problem. Let's go on to the next question. We've got a concrete wall with an expansion joint every 40 feet. And the thermal coefficient of expansion for concrete is 6 times 10 to the minus 6th. Question is, how much will each panel expand when the temperature is 1 degree warmer? All right, so we're looking for deformation, delta. Do we know our equation? Sure. Coefficient times original length times delta T. All right, what are we given? We are given the thermal coefficient of expansion for concrete. There it is. We're given the length, it's 40 feet. Notice that's in feet. Should we convert that to inches? Why, yes, we should. So 40 feet times 12 should give us, what, 480 inches. And then, do we have delta T? Yes. The question is, when delta T is 1 degree Fahrenheit, how much does it grow? So we can plug all those numbers into our good old equation. Going on to the next question, same wall, same 40-foot sections, and same concrete. Now the question says, when the temperature is 80 degrees Fahrenheit outside, the ends of the wall just touch. Question is, how big will the gap between them be when the temperature is 20 degrees Fahrenheit? So what are we looking for? We're still looking for deformation, change in length. There's our good old equation. What are we given? We still know the coefficient. We still know the length. It's 40 feet, and we're going to convert that to inches. And do we know delta T? Well, sort of. We can figure it out. We know that the original is 80 degrees. The finished temp is 20 degrees, so delta T will be 80 minus 20. Delta T will be 60 degrees. Now we have all the numbers we need to plug into our equation. Let's think about good old railroad tracks. So here's a section of track where the segments are 60 feet long. We know the coefficient of steel, thermal expansion of steel. Question is, how much does each section of rail lengthen when the temperature is 1 degree warmer? All right, so we are trying to find deformation again. There's our good old equation for figuring out deformation due to thermal expansion. And what are we given? There's our coefficient of thermal expansion for steel. We're given the length. Now that's in feet. Should we convert it to inches? Why, yes, we should. 60 feet times 12 should be 720 inches. And do we have delta T? Yes, it's 1. So now we can plug all our numbers into our equation and find out how much the rail lengthens when it gets 1 degree warmer. Let's go on to the next question. This one kind of turns it on its head a little bit. So here are these same rails. They're laid in cold weather with a 1/4 inch gap between them. The question is, how many degrees of difference will cause the ends of the rails just to touch? All right, what are we looking for now? We're looking for delta T. We're given the length, and again, we're going to convert that to inches, 720 inches. What else are we given? We've got the deformation. We're looking for how much causes it to expand 1/4 of an inch. And we've got the coefficient of expansion. So here's our thermal expansion equation, but let's rearrange the terms because we're looking for this term, delta T. If we want that term by itself, let's divide both sides by coefficient times length. The coefficients times lengths cancel out, and we're left with deformation divided by coefficient times length gives us delta T. And now you can just plug those into your calculator. Last question is related to the previous question. So they're laid with a 1/4 inch gap when the temperature is 70 degrees Fahrenheit. At what temperature will the rails touch? Now in the previous question, you figured out how many degrees of difference was that. And I think, if I remember right, I should have written this down, I think you found 53.42 degrees. Question is, at what temperature will the rails touch when you're looking at the thermometer? So you're trying to find the final temperature. You're given the initial temperature, delta T you figured out from the last question, and so to figure it out, you'll start with the initial temperature, 70 degrees, plus delta T, 53.42, to tell you what is the final temperature when the rails just